Welcome, dear friends. Continuing with the concept of entropy, I would be starting my discussion with the poll question, which I had left midway in the last lecture. Okay, you must have given some thought on it. We are discussing some very elementary kind of concepts in entropy before we take up the derivation of the property of entropy. So I would be launching my first question, and then we would start with the discussion. Okay, so you think upon this question and try to answer it as correctly as possible. Okay, so I launch this question. So the question is about heat addition process, and we are trying to figure out whether during the heat addition process, which is isothermal, the entropy remains constant or whether it increases or whether it decreases. Okay. Please note that we are not talking about any heat addition process. We are talking about the isothermal heat addition process. Okay. And when I'm saying isothermal, I mean the constant temperature process. Okay, constant temperature process. So let me close this poll and show you what the students have answered before I take up the discussion on this. Okay. So I'm closing this poll now. About 90% of the students have answered this poll. Right, and the question is as follows: Okay, that uh, we are asking what would happen to the entropy during the heat addition process. So I'm closing the poll and I'm sharing the results. Okay. So you see that about 66% of the students they feel that during isothermal heat addition process the entropy increases, and they are right. Okay, and they are right. Okay, so let me explain you this before I. Okay, so whether the whiteboard is visible to you, the whiteboard is seen. Not yet. Now it is seen. Okay. All right. Thank you, Gavi. Okay. We would be discussing this question. The question was when the heat transfer is happening. Okay. Where there is a heat transfer to the system from the surrounding, what would happen to the entropy? And the second part of the question is, if the heat transfer is isothermal, then still whether the entropy would increase. So as I was discussing in the last lecture, that whenever we are talking about heat transfer, essentially, okay, whenever there is a heat transfer, essentially there is an entropy transfer. Please mark my words. Please mark my words that whenever there is a heat transfer, it is associated with entropy transfer. It means that the meaning is when you are transferring the heat from the surrounding to the system, the entropy also gets transferred. Okay, so along with the heat flows the entropy. Along with the heat flows the entropy. So when there is a heat transfer to the system, the molecular disorder would increase, and that would increase the entropy. Right now, the question is, so whenever there is a heat transfer, it would increase the entropy. The second part of the question is, suppose we consider a special case of heat transfer, namely the isothermal heat transfer, So I want to ask you this question, that can we imagine a process, where we are transferring the heat to the system? Okay, we are transferring the heat to the system, and the process remains isothermal. I mean to say that you are adding the heat and the temperature does not change. Can you think about this kind of process? Okay, please answer if you got my question. My question is, can you think of certain process, or can you visualize that you are adding a heat to a system, and its temperature remains constant, and its temperature still remains constant? Is this possible? Yes or no? Vedant is saying adiabatic. No, 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 no. Adiabatic means, then if you are saying it's adiabatic, then there would be no heat transfer. If you are talking about adiabatic means there is no heat transfer. So Vedant, that is wrong answer. Sharavari is saying that it is not possible. Okay, Sharavari is saying that it is not possible. Gargi is saying it is not possible. Parikshit, what he is asking, I'm asking that whenever there is a heat transfer to the system, okay, is it possible that the temperature of the system remains constant? So there are some students who are saying, almost those who are answering, they are saying that it is not possible. Vedant is saying it's not possible. Neha is saying it is not possible. Isothermal means the temperature remains constant. Isothermal means the temperature remains constant. Okay, so I want you to think of a process wherein you are having a heat transfer and still the temperature remains constant. Can you think of such kind of processes? Whether such kind of process is possible or it's impossible? Ganesh is saying it's possible in reversible engine. How it is possible? Ganesh? How is it possible? I am talking about only a process. Okay, how is it possible? Can you explain that? Gunjan is saying it is possible in reversible process. How, Gunjan? Samir is saying it is not possible. No, temperature difference is needed. No, we are not talking about that, Samir. Temperature difference obviously has to be there. Means the surrounding would be at certain temperature, system would be at certain temperature, and there has to be certain temperature difference for the heat flow. Okay, my question is not that. My question is, can we imagine a process where we are transferring the heat? Okay, we are transferring the heat to the working fluid and to the system, let us say, comprising of working fluid, and its temperature does not change. Atharva Pandit is saying that temperature is in reversible engine, sink and source can supply infinite heat. No, that is correct. I am not talking about the temperature of the reservoirs. Obviously, temperature of the reservoirs would not change. Okay, the sink and source temperature. You are correct, Atharva, that the temperature of the reservoirs would not change if you reservoir. I am talking about process. I don't know how it is possible mind, and is separate on how it is possible in Carnot. Okay, without wasting much time now, I guess that I need to answer this question. Okay, so look at this now. Okay, I'm answering this question now. Let me rub this. My question is whether it is possible to have a heat transfer. Okay, have a heat transfer and still the temperature remains constant, Okay, so what I would be doing is, look at this. As I said that obviously whenever we are talking about heat transfer, there would be an entropy transfer. So this is the system. This is a system. Okay, this is a system, and this system has, let us say, some gas in it, right? And you are transferring the heat. Okay, you are transferring the heat here. Okay, so when you are transferring the heat, and I want this process to be isothermal. I want this process to be isothermal, meaning that the temperature should remain constant. Okay, so what I would do is that whatever is the heat being transferred. Okay, so let me apply the first law of thermodynamics to the process of heat transfer. Let me call that process as process 1 to 2. Okay, process 1 to 2. I am now trying to visualize the process, isothermal process of heat transfer, isothermal heat transfer process. Heat transfer process, process 1 to 2. Okay, and now when there is a heat transfer to this gas, so let me apply the first law of thermodynamics to this. So for this process, I am applying the first law. Q 1 to 2 is equal to delta E plus W 1 to 2. Now for the process to be isothermal, the requirement, okay, how does this equation get modified? For the process to be isothermal, how this equation gets modified? Can somebody answer this? For the process to be isothermal, how does this mathematical statement of first law of thermodynamics gets modified? What would be that statement? How would this change? No effect. Sairaj is saying latent heat supply temperature is not changing. Okay. No, that is all right. I am asking you that how to rewrite this equation. How to rewrite this equation when the process is isothermal? How do I rewrite this equation when the process is isothermal? Sairaj, how to rewrite this equation? This equation I had written. I want to rewrite this equation now when the temperature is constant. Okay, the temperature is constant. Means I want the process to be isothermal. So for an isothermal process, how does this equation change? How does the equation change? Okay, Sairaj is saying change in E is 0. Correct, correct. Selva, you are correct. Right. Okay, so it means that for the process to be isothermal, the change in internal energy has to be 0. Then the change in internal energy has to be 0. So this term becomes 0. This term becomes 0. Okay. So it means that whatever heat we are supplying, gets converted to work. It means that the piston would displace. Okay, it would move away from the top dead center, and the gas would expand. The gas would expand in a manner such that what is converted to expansion work. So a process, an isothermal heat transfer process is possible, and third, when the heat does not go in internal energy of the heat which is transferred during an isothermal heat transfer process. The heat which is transferred into an isothermal heat transfer process. Am I audible now? Okay. Uh, uh, heat goes not to heat is not utilized for increasing the internal energy. It is used for producing expansion work. Okay, so the heat transfer can be isothermal when you get expansion work such that the change in kinetic energy is 0. Okay, and that is what happens in the Carnot engine. Okay, somebody was saying that it happens in the Carnot engine, and during the process one, and what happens, gas so to this process in the Carnot engine, so the process 1 to 2 involves an expansion from volume V1 to volume V2. Okay, volume V1 to volume V2. Is this clear? Uh, Okay, there were some issues about the audio. I would be repeating this point again. Okay, but because there were some issues with the audio, I had launched the second question. So you answer the second question, and I would be repeating the concept again, in assuming that my voice was breaking in between. Okay, so you answer this poll question. The question is seen. Whether the question is seen. Hello, 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 Billy ma'am. Can you share the question from your side? Billy ma'am, can you share the second question? You are not able to do that? Okay. All right. Let me try another question. Okay, Gavi, I have question. Maybe to with my discussion process. You process is adiabatic when there is no heat exchange of the working fluid with the surrounding. The process is normal if the temperature remains constant. The temperature remains constant. Okay. And yeah, Kunal, I'm aware that there are some issues with the voice. Kunal, I'm aware that there are some connectivity issues. Okay, you are not able to hear my voice clearly. Okay, but I will be trying to be as loud as possible. Okay, all right. Most of you answered this correctly. That during an adiabatic process, the heat transfer is zero. Okay, so I was discussing this. Sorry. Can you see the whiteboard now, Kunal? Abhijit? Okay, Vedant, thank you. Am I audible now, Vedant? Gargi? Okay, thank you, thank you. There were some issues. I would explain that concept again. See, I was talking about okay, what Parikshit is asking, will entropy be constant for adiabatic as well as reversible process? Yes, it would be constant, Parikshit, it would be constant. Okay, why, that would see later. So when I am talking about a reversible, I'm talking about a heat transfer which is isothermal, okay. So as I said that whenever there is a heat transfer, there would be an entropy transfer. Whenever there is a heat transfer, there would be an entropy transfer. And in a Carnot engine, during the process 1 to 2, of a Carnot engine, what happens is that there is a heat transfer, but the temperature remains constant. And why is that happening? Why is that in spite of the heat transfer, the temperature is remaining constant? The reason is the gas expands. Okay, the gas expands, and it expands in a manner such that the change in internal energy is zero. It expands in a manner such that the change in internal energy is zero. It means that Q12 is equal to W12. Q12 is equal to W12. Okay. So in the Carnot engine, the process is isothermal and process is reversible. That is correct, and it is an expansion process. Okay. So it is an isothermal heat transfer expansion process. Okay, and that results in increase in entropy. Okay, so 1 to 2 process is reversible, isothermal, and it is an expansion process. Okay, now you know that if the process is adiabatic, okay, that means if the process is adiabatic, the heat transfer is zero. Okay, suppose you are talking about the same piston cylinder arrangement. Okay, let me draw it again. And when this process becomes adiabatic, it means that Q is equal to zero. Okay, so process 2 to 3 in the Carnot engine, for example, process 2 to 3 in the Carnot engine is the process where the heat transfer is zero. Okay, so when the heat transfer is zero, it means you call it as an adiabatic process. Okay, so this equation gets converted to Q 2 to 3 is equal to W 2 to 3. Okay, W 2 to 3. Now what can you say? About the internal energy? What can you say about the internal energy when Q is equal to 0? When Q is equal to 0, why is Q 0? Because we are talking about a process, okay, in the Carnot engine, which is adiabatic, reversible adiabatic, right? So when the process is adiabatic, what would happen? To the internal energy? Try to answer this question. When the process is adiabatic, what would happen to the internal energy during the process 2 to 3? We are talking about a Carnot engine. What would happen to the internal energy? We are talking about a Carnot engine. Okay, try to answer this. During the process of expansion, which is process 2 to 3, what would happen to the internal energy? Any answers? In the Carnot engine, during the process 2 to 3, which is a adiabatic process, what would happen to the internal energy? Okay, Selva is saying it would decrease. Anybody else has answer? And what would happen to the, Darshan is saying that it would decrease. Darshan Tambori. Okay, Gargi is saying it would decrease. Darshan, Selva, Yugandhara is saying it would decrease. What would happen to the temperature? What would happen to the temperature and internal energy? What would happen to the temperature and internal energy? No, that would change. That is correct, Sairaj. But what would happen? Whether it will increase or decrease, Sairaj? So during expansion, see, when you are talking about an expansion process, when you are talking about an expansion process, which is adiabatic, okay, the internal energy would decrease. Okay, internal energy would decrease. Rushal is also saying it would decrease. Correct. Most of you, those who answered, they are correct. The internal energy would decrease. Okay. Vedant is also answering it correctly. What would happen? Okay. What would happen to the temperature? What would happen temperature? So you see that the temperature is going to decrease. The temperature is going to decrease, right? Temperature is going to decrease. The volume is going to increase. The volume is going to increase. So this is the process 2 to 3 in the Carnot cycle, right? So what would now happen to the entropy? What would now happen to the entropy? Let me ask you this question in a different form. Let me put a poll question there. I'm asking this question. Okay. During adiabatic expansion of the gas, what would happen to the temperature? Adiabatic expansion of the gas, what would happen to the temperature? Now, some students are saying that the temperature remains constant because the process is adiabatic. Some students are saying that the temperature is going to increase because the process is adiabatic. And some students are of the opinion that the temperature of the gas would decrease. Temperature of the gas would decrease. So the majority of the students are saying that it is decreasing, and they are correct. Actually, there is no reason. There is no reason why the temperature would increase. There is no reason why the temperature would increase, because first is the process is adiabatic, so there is no heat transfer. That is one thing, and second is there is an expansion. There is an expansion. So there is no reason. There is no reason why the gas temperature would increase. And I'm surprised to find that some students, and not it is not a small percentage, about 26% of the students who are answered, okay, they are saying that the temperature of the gas would increase, okay, which is totally wrong. Okay, uh, again, a similar proportion of the students are saying that it would remain constant, which is also wrong. Okay, I had just shown you, and I'll just close the poll and I would show you the results. I'm sharing the results. Okay, so you see that what is the question asked. So what would happen during adiabatic expansion of the gas? What would happen to the temperature? So the correct answer is the temperature of the gas would decrease. The temperature of the gas would decrease, and it is not that the temperature would remain constant or it would increase. And why is that so? Let me hide this, and you can see the screen now, right? So what you see is that if I talk about the process 2 to 3, 2 to 3 is equal to change in internal energy plus W2 to 3. Now, when this is adiabatic, this equation gets modified to like this: Q is equal to 0, Q is equal to 0 is equal to delta E, delta E plus W2 to 3. It means that W2 to 3, W2 to 3, that the delta E would decrease, delta E would decrease, and when the delta E decreases, the temperature would decrease, temperature would decrease. Okay, right? So whenever we are talking about expansion which is adiabatic, when you are talking about an expansion which is adiabatic, okay, and in my ideal engine, let us say it is also a reversible adiabatic expansion, this would result in a drop in temperature. Okay, now this is a Carnot engine. Now let me imagine that there is a process. Okay, I am imagining a process uh, which is again adiabatic, and that is a compression process. Okay, when you are saying compression process, what would have happened to the volume V3? What would happen to the volume V3 when you are talking about compression process? See, you are having an expansion from V1 to V2, that is an expansion, and there is a heat addition. Then there is a expansion from V2 to V3, right? And now let us imagine that there is a compression from okay, like this, sorry, compression from V3 to V1, such that there is no heat transfer, and you get back to the initial state, right? Yes or no? Okay, so now what I have imagined is a cycle. Look at this cycle. This cycle has three processes. One is isothermal expansion process. Okay, I am considering an ideal engine, so it is a reversible isothermal expansion process, wherein there is a heat addition, wherein the heat is being supplied. The next process is again an expansion process, wherein the volume increases from V2 to V3. Right? Now I am imagining the third process, wherein the volume changes from V3 to V1. Yes or no? Correct. So this becomes a thermodynamic cycle. Right? Whether this is a thermodynamic cycle, it is a thermodynamic cycle. Okay, so this thermodynamic cycle produces certain work. Okay, so the hatched area which you see, that is the work output. Of a thermodynamic cycle, having three processes. Which are the three processes? One is a reversible isothermal expansion. Second is a reversible adiabatic expansion, followed by a reversible adiabatic compression, followed by two adiabatics and one isothermal. So I am imagining a thermodynamic cycle. Okay, which is having three processes. One is isothermal, followed by a adiabatic expansion, again followed by another adiabatic process, which is a compression process. Okay, whether this kind of thermodynamic cycle is possible, yes or no? whether such a cycle is possible. You answer this question, whether such a cycle is possible. Garge is saying it is possible. Tanay is saying that it is not possible. Sairaj is saying it is not possible. Vedant is saying not possible. Gaurav is saying it is not possible. Omkar is saying it is not possible. Vivek also has the same answer. Anybody who has a different answer? Okay. Garge is saying it is not possible. Okay, Tanay is saying it is violating the second law. Okay, good. I see that some students are really studying hard. Okay, but I want more number of students to answer. Ritesh says it is not possible. See, I want you to listen to the videos which have been shared to you. The reason is twofold. One is there could be connectivity issues during online lectures, and it might be that you are not able to appreciate the concepts better in the online lectures. So we are following uh, a double strategy of explaining you. One is you can watch the online lectures at your the videos at your pace. Whenever there is connectivity, you can watch those, and then you can come prepared for the lectures, online lectures, and try to answer those concepts which are asked in the poll form. Okay. So basically, Ritesh is saying it's not possible. So it is not possible, and why it is not possible? Let me answer this. And yes, some students have already know the answer, but I want that the entire class should understand this. Okay, so this is not possible because look at this. Okay, this arrangement. I'm rubbing this a bit. So first thing is, the question is whether this cycle wherein there are two reversible adiabatics, okay, following each other. There are two reversible adiabatics following each other, meaning that they are intersecting with each other. You see that they are intersecting at the point 3. There are two reversible adiabatic processes which are intersecting with each other. Okay, uh, and and there is a isothermal. Okay, which is which is which is a thermodynamic cycle, which becomes a thermodynamic cycle. Okay, so this cycle which involves two reversible adiabatics end to end. The cycle which involves two reversible adiabatics end to end, it means that they are intersecting, is not possible because you see that this cycle comprises of some engine. Okay, this cycle is comprises of some engine, and this engine, you see, if you draw a schematic of this engine, what is this engine doing? This engine is exchanging heat with the reservoir which is at a temperature T. Temperature is T of this reservoir. Okay, so the working fluid of this engine is accepting the heat during the process 1 to 2, okay, and that is the isothermal, and this engine is producing certain work. How much is the work which is being produced? This work which is being produced is equal to the area which is enclosed by 1, 2, 3. This engine is producing work which is equal to the area 1, 2, 3, and heat rejection is 0, because you see that it is exchanging heat with a single reservoir. So this violates this violates the Kelvin Planck statement of second law. This violates the Kelvin Planck statement of second law, and hence this is not possible. What is not possible? It is not possible to have. It is not possible to have two reversible adiabatics. Okay, intersecting with each other. Let me ask a poll question. Some students are saying it is false. Why is that so? What did I prove now? I had proved that the two reversible adiabatics cannot intersect each other. What I have proved is two reversible adiabatics cannot intersect with each other. They cannot intersect with each other. That is what I had proved. Okay. Two reversible adiabatics cannot intersect with each other. That is proved. Okay, let me close this and share the results. Yes, the answer is true, and 90% of the students have got this right, that two reversible adiabatics cannot intersect with each other. Okay, so that is the right answer. So let me hide this. Do you want me to repeat this or no? Do you want me to repeat this or no? Not the usual names, but somebody else should say. Okay, most Kunal wants me to repeat. All right. Anybody else wants me to repeat? Kunal wants me to repeat. Anybody else wants me to repeat? Okay, Abhijit also wants me to repeat. Okay, all right. It means that there are few at least. So these are representative opinions. I'm understanding that this requires a repetition. Okay. For those who understood this, no problem. It would be sort of revision. Okay. What I am going to prove now is that two reversible adiabatic processes cannot intersect with each other. Okay, cannot intersect with each other. Okay, that is what I'm going to prove. Okay, what is to be proved? That two reversible adiabatic processes cannot be intersecting. Now what I'm assuming is on the contrary. Okay, I'm assuming on the contrary. Contrary means opposite. What I'm assuming is that it is possible to have two reversible adiabatic processes. So in my diagram you see that the process 2 to 3 is a diabatic process, because you see Q is equal to 0, and process 3 to 1 is an adiabatic process, that is heat transfer is 0. So I am imagining that it is possible that these two processes, they follow each other. It means that they intersect, they have a common point, which is point 3. Okay, when I'm saying it is a common point, the meaning is that it means that they are intersecting. Okay, it means that one process is followed by the other process. So I am assuming that these two processes are intersecting. Process 2 to 3 and 3 to 1 are intersecting at 3. Okay, actually I want to prove that this is not possible. I want to prove that this is not possible. Okay, so let me assume on the contrary that they are intersecting. Now, what I am assuming is the cycle wherein there is a process 1 to 2 of expansion, which is isothermal expansion process, a reversible isothermal expansion process, similar to that in the Carnot engine. Okay, wherein the piston moves away from the top dead center. You see that suppose this is a top dead center, piston is moving away from the top dead center, so the pressure is decreasing, volume is increasing. The next process is also an expansion process, which I had explained to you that this would be followed by temperature drop. So temperature would drop down from T2 to T3, and the volume would increase from V2 to V3, and the heat transfer would be 0. Why the heat transfer would be 0? Because it is a adiabatic process. Again, the next process I am saying that it is again adiabatic, heat transfer is 0. But now in this case, I am imagining that there is a compression from V3 to V1. Sorry, I am imagining that there is a compression from V3 to V1. Okay, so this becomes a thermodynamic cycle. This becomes a thermodynamic cycle. How is that? Having three processes, process 1 to 2, where there is a heat supplied. So heat is supplied from process 1 to 2. So let us say that heat is supplied from a source which is at a temperature T, and that temperature T is constant. So the engine is accepting the heat at a constant temperature T. Temperature remains constant. Heat transfer is, let us say, Q12. The next process of this engine is expansion process. Okay, and then there is a process of compression. Okay, now this is a pressure volume diagram, and you know that the significance of pressure volume diagram is that the area enclosed by the pressure volume diagram is the work. Area enclosed by the pressure volume diagram is the work. So this hatched area which I have shown you, this hatched area is the work transferred or work produced by this engine. It is the net work produced by this engine. Okay, so this engine having three processes 1 to 2, 2 to 3, 3 to 1. This engine is producing work equal to the area A123, hatched area. Okay, and how much is the heat being rejected? The heat rejected is 0. Heat rejected is 0 because it is exchanging heat with a single reservoir. So this becomes an engine which produces work while exchanging heat with the single reservoir, which is not possible because that is a violation of Kelvin Planck's statement of second law. That is a violation of Kelvin Planck's statement of second law. Okay, so this is not possible, right? This is not possible. So when this is not possible, whatever we had assumed is not possible. What we had assumed? We had assumed that the process 2 to 3 and 3 to 1, they intersect with each other. Process 2 to 3 is adiabatic and process 3 to 1 is adiabatic, and these two adiabatic processes, reversible adiabatic processes, have a common point 3. In other words, we cannot have two reversible adiabatic processes which are intersecting, or in other words, we need to have the processes which are reversible adiabatics which are parallel. Okay, they need not intersect with each other. Okay, when can they not intersect? They cannot intersect only if the process 2 to 3, that is reversible adiabatic, and another process which is a reversible adiabatic, they are parallel to each other. Okay, I hope this is clear to you. If it is clear to you, please answer yes. Yes, Abhijit is saying yes, understood. Kunal, you understood? Abhijit, yes. Got it. Yes, Kunal has got it. Gargi has got it. I hope most of you have got it. Okay. Gauri has got it. Vedant, Gauri, Samir, Tejas has understood. All right. So this is the first part of the proof. Now what we are trying to do is that in the next class, what I would be doing is that I would be deriving the property of entropy. I would be deriving the property of entropy, and the derivation starts from this first proof. There are set of proofs which would lead us to the property of entropy logically. Okay. So first proof was that you are proving that there are two reversible adiabatic processes, and those reversible adiabatics cannot intersect with each other. In the next two proofs, I would then go on to say that there exists, finally I would say that there exists a property which is called as entropy. Okay, how is that proved logically? You should see the videos also and make sure that you understand that, and also we would be discussing in tomorrow's lecture. Okay, the Clausius theorem. Okay, thanks for joining. Have a good day. Bye for now.